about time I do that.
You can write it on?
Oh wait, I think you have a webcam.
Yeah, I'm not going to mess with it though, unfortunately. Okay, so
Okay.
counting. We know how to count. We're going to hop into our awesome little car, and it's got 3 digits in it. Our odometer starts off at 000. We drive a mile, 001, 002, 003. Don't type in all these notes. I'm going to be typing in vast numbers of sequences like this. That would get real tedious for you to write. All right, so we've driven 9 miles. We're going to drive 1 more mile. Something magic happens. Our counting system is base 10, meaning that we have the digits 0 through 9. So this is maxed out. It can't get any higher. There's no digit higher than 9. So it resets back down to the minimum. That 0 becomes, that 9 becomes a 0 in the next column, increments by 1. And yeah, we know this. We learned this like in the 1st or 2nd grade or something like that. But we don't usually think of it in terms that we've maxed out this value, and so we had to increment the next one. How did we know we had hit the max value? Because it's base 10, and base 10 supports 0 through 9. So if you were using something else like base 5, for some horrible reason, then the max digit would be 4. You could use the digits 0, 1, 2, 3, 4 if you were on base 5. We're not going to do base 5. That's just an example. And then if you kept counting, right, really, you don't have to type in all these numbers. You know, when you got to the point of 99, it's maxed out again. It can't get higher. There are no digits higher than 9, so that one resets back down. That one increments. Yep, you know what's going on. So he's maxed out, so he's got to reset back down to the lowest, and we add 1 to the next one, and so on. And then if we kept going and we got to 999,
We can't do it anymore.
yep, that's data overflow, right? It resets back to 000, and kaboom, we've lost some data. That's overflow. We've exceeded the number of the data that could fit in those digits.
Actually,
Now that's a decimal.
My lecture on here.
So we have base 10 is also known as decimal. Decimal, DEC means 10, just like octagon has 8 sides and a hexagon has 6 sides. A decagon would be something with 10 sides. So that's good old base 10. So what if we have this number here, 2019 in base 10? What does that really mean? This is place values. That's the ones place. That's the tens place. That's the hundreds place. That's the thousands place. And there's a reason for me saying this stuff, because I know you know it, but we're then going to apply it to other counting systems besides base 10. So if that's the thousands place, that's 10 to the power of 3. I'm going to use the Python notation, even though it doesn't work in this language. And then that one is 10 to the power of 2.
10 semicolon 3.
Yeah, there's just no way of doing it in C++. We could use a POW function, but I'm absolutely not going to write POW 10, 3 up here to indicate place values. And that's 10 to the power of 1. And this is 10 to the power of 0. And yeah, normally I would have used the uppercase little caret instead, but, you know, like that. But, okay. So, that's 1,000. That's 100. We know that. That's a 10. And that's a 1. What does it mean to take something to the 0th power? It's a weird concept, something to the 0th power. Any number to the 0th power is 0. 8,372 to the power of 0 is, excuse me, did I say 0?
1.
1. Yeah. You know, 8,372 to the power of 0 is 1. Negative 10 trillion to the power of 0 is 1. And there's a mathematical proof that I could write up here if I could quite exactly remember it. But I don't, so I'm going to not mess with it. Let's go on from here. So if we have the number 2,000, 0, 1, and 9, if we were going to express this in some incredibly long form, we would say that this is 2 times 10 to the power of 3 plus 0 times 10 to the power of 2 plus 1 times 10 to the power of 1 plus, and this gets tedious, 9 times 10 to the power of 0. Or in other words, 2 times 1,000 plus 0 times 100 plus 1 times 10 plus 9 times 1, which of course is 2,000 plus 100, nope, plus 10 plus 9 equals, lo and behold, we have converted from base 10 to base 10. Big accomplishment. But what we've reminded ourselves is that these are powers of 10. You know, and the exponent is just the number of zeros after it, right? 10 to the power of 1 is a 1 with 1 0. 10 to the power of 2 is a 1 with 2 zeros. 10 to the power of 79 would be a 1 with 79 zeros behind it. All right, we're going to switch over to some other counting system. Base 4. No one would ever use base 4, but you could. Base 4 would have only 4 digits, 0, 1, 2, and 3. So we hop into our base 4 mobile. 0, 0, 0, 0, 0, 1, 0, 0, 2, 0, 0, 3, 0, 0, 4. Nope. We've maxed it out. So somebody tell me what that's actually going to do.
Gonna hop on.
Yep, it's going to hop to the next one, add 1 to the next column. So the 3 became 0, and then the next column was incremented by 1. So we drive another mile in our base 4 world. I guess this is a world where everybody had only 2 fingers on each hand. I don't know. 0, 1, 2, 0, 1, 3, 0, 1, 4, but that doesn't work. That one resets down to the minimum, and that one increases by 1. And so on. And when you got down to that, what would happen when you drove 1 more mile? What would it become?
1, 0.
Yep, it would become 1, 0, 0. Just like 99 changed into 100, 33 changes into 100. So when we look at 0, 1, 2, it doesn't always mean 12, right? It only means 12 in base 10. If we were going to put the base 10 equivalents, you know, that's the same as a 0, that's the same as a 1, that's the same as a 2, that's the same as a 3, that's the same as a 4, that's the same as a 5, that's the same as a 6, a 7, and an 8, and so on. So 0 to 0 in base 4 is equal to 8 in base 10. All right. If we were going to have multiple digits, like if we wanted to know what 2012 base 4, which I'm now going to start abbreviating like this, if we have that number in base 4 and we want to convert it to base 10, which I could also do parentheses, 10 after it, then we have to write down the powers of 4. 4 to the power of 3, 4 to the power of 2, 4 to the power of 1, 4 to the power of 0. Well, I hope I can remember. 4 to the power of 0, what is that? Anything to the power of 0 is, did I hear someone say it? 1, yep. And so 4 to the power of 1 is just 4. What is 4 squared? 4 squared, 4 times 4, somebody blurt it out.
6.
Yep, and then 4 cubed would be 64. Okay, so if we have that number, 2012, that means
I'm gonna change
2
this to
times
9s.
64 plus 0 times 16. You see where I'm getting these numbers.
1.
Plus 1 times 4 plus 2. And then I could add that all up, right? That's 92 plus another 16 plus whatever, I don't know. Not 92, 64 doubled is 128 plus 4 plus 2, so that's 134. If I did that right, that's 134 in base 10. All right, some folks weren't watching me, so I ought to write down another base 4 number and make you do the conversion. But I'm not gonna. I do want you to start watching though, because now we're getting to the really important stuff, which is binary. Hop in our binary car. Say we have 4 digits of binary. Binary is base 2, which is only zeros and ones. All right, so 0, 0, 0, 0, 0, 1. Can we do 0, 0, 2? Nope, we've already maxed out. There's no digit higher than 1, so what does that become?
0, 0, 1, 2.
Yep, 0, 0, 1, 0. I'm only hearing like 2 people say stuff, so I hope I don't have to start calling out names to get other people to volunteer information.
So
Then what happens? 0, 0, 1, 1. Then what happens?
0, 0, 2.
Well, there's no 2s.
2, 1, 0, 0, 2.
We have maxed this one out. It can't get any higher.
0, 1, 0.
Yep, just like rolling over your car at 99 miles an hour. And then it 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1. And then the whole thing repeats except with this bit changing to 1. Yep, so it becomes 1,000 and it continues counting from there.
1,000, 100, 1,000, 100.
Yep, so let's do it. 1,000, 1,001, 1,010, except it's not really 1,000. That's base 10 talk. But yeah, that's how we, that's how we think of it when we look at it.
So we got to repeat the whole thing, pretty much.
There we go. Right, we repeated the whole thing except the next one was set. And if we needed, to do a 5th one, we'd go through the entire cycle again, but with a 1 in front of them rather than a 0. So that's 4 bits. A bit is a 0 or a 1. That's how the computers track information, by the absence or presence of current in some little piece of silicon inside it. Or if it's writing it out to a CD-ROM or a DVD-ROM by, burning something into the aluminum substrate, so that if it's marked with a pit, it's a 1, and if it's smooth, then it's 0, or something like that. And back when you had, acoustic modems and they'd squeal when you dialed on to American Online or whatever, certain sounds meant, zeros and other sounds meant ones. So we have these 4 bits. That's a 4-bit number. A bit is the smallest piece of information a computer can handle. Just means 0 or 1, false or true, no current or current, no electricity or electricity. If we counted these out, we'd find out how many numbers we can store with 4 bits. Right, that's a 0, that's a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Hope I haven't done this wrong and I have to change them. 11, 12, 13, 14, and 15. So the highest decimal, the highest base value, base 10 value you can support with 4 bits is 15. There's a mathematical formula that'll give you that. What about if you only had 3 bits? The maximum value you could support with 3 bits would be 7. The maximum value that you could hold with 2 bits is 3. The maximum value you can hold with 1 bit, well, that's silly, but it's 1, right? There's a formula for that. So 1 bit can hold a 1, can count to 1. 2 bits can count to 3. 3 bits can count to 7. 4 bits can count to 15. Now that's not counting 0, right? When we say we can count up to 15, if you include 0 in your range, that's 16 possible values, right? Or if you're counting from 0 to 7, that's 8 possible values. That kind of gives you the clue as to how these could be calculated. 2 to the power of n, where n is the number of bits. tells you how many what the possible range, the number of combinations you have. 2 to the power of 1, that's 1 bit, right? 1 bit can go up to 1, equals, 2 different possibilities. 2 to the power of 2, 2 bits give you 4. 4 different possible values, 0, 1, 2, and 3. 2 to the power of 3, because you have 3 bits.
Can give you 8.
Yep. 2 to the power of 4. Now, I'm not going to keep going 5, 6, 7, and 8. I'm going to skip to 8, and then 16, and then 32, and 64. So 4 bits can give you up to 16, 0 through 15. 16 different possible values. 2 to the power of 8. 2 to the power of 8 is 256. So the highest value that can be stored in 8 bits is 255. How about 16? So your old Nintendo, or your father's Nintendo, or whatever, right? The 8-bit computer, or the Apple II, or the Commodore 64, all those things. All those things, during the 70s and the 80s were 8-bit computers. And so they were limited. For example, they had 8-bit graphics in them, meaning that they could only pick one of 256 different colors to display on the screen. So the drawings were real primitive. You didn't have photorealistic, Donkey Kong. He was drawn in only a certain few colors. Most of them couldn't even support 256 colors. They could just have a palette of like 16 colors that were drawn from a larger set of colors that could be used. So everything on the screen was done like in 8 colors or 16 colors. And those numbers are all based on the powers of 2. So an 8-bit video card could only display 256 different colors. And there were video cards like that in the 80s. They didn't look real good. And if you have CGA graphics, and you see an example of it, they did not support a whole bunch of colors. It looks like they're only supporting 4 colors, but from a larger palette. But I see white, black, cyan, and magenta. Right, so there's only 4 different possible values, meaning that the graphics card, each pixel was controlled by 2 bits. So it could have 4 different possible values. And then maybe there was a table somewhere that said, if this bit is a 1, then it's magenta, and if this bit is 2, it's a cyan, and if this bit is a 3, it's a white, and if this bit is a 0, it's a black. Something like that.
It was more than that, right? It was like the chemical, like was on the TV.
Well, yeah, it goes, yeah. That's a different matter though. How colors get displayed based on luminosity. Your TV has, each pixel, each phosphor has 3 different colors in it, right? RGB, red, green, and blue. And the mixture of those, like no red, no green, no blue, is solid black. All red, all green, all blue, and they're all maxed out as white. And then you have, a whole bunch of different combinations of colors in between. So the number of bits dictates things like the number of the max RAM that could be installed in that computer. For example, the Commodore 64 could hold up to 64 kilobytes, which is 64,000 bytes. And it's actually 65,535, but the difference between a kilo in computer science and a kilo in physics are a little bit different. So anyways, 2 to the power of 16. You've trashed your old Nintendo because it wasn't cool enough and you bought a Genesis or a Super Nintendo. 16 bits. That can display
65,500.
65536. So any pixel on a color on a Genesis can be one of 65,000 different colors. That's a 16-bit graphic card. What if you have a 2-bit graphic card? Those were really cool in the late 80s. Wow, I bought a Mac Pro with with a 32-bit video card so it could display thousands of colors. Let's calculate 2 to the power of 32. I don't have it memorized. 2 to the power of 32. Ooh boy, that's a big number. let's space this out. Yes, sir.
Was it easier to run video games that had less pixels?
Well, I don't know.
Like Super Mario Bros. Which is
Yeah, people who did those video games went to a lot of trouble to use clever shading techniques to make the graphics look good. They used what's known as dithering, which is where you have dots of the two different kinds of colors mixed together to produce a third kind of shading. And so some people say that those old video games look best on an old-fashioned phosphor monitor rather than an LCD, because they were programmed to take advantage of very specific color combinations. So we have our good old 32-bit values going up to, I believe that's 4 billion. Yeah, about 4 billion. What about 64? You have a 64-bit. Now I know you've heard of like 32-bit Windows versus 64-bit Windows. 32-bit Windows, a program on it could access at most 4 billion bytes.
64-bit connects as
Way larger.
and it's 1.844674407.
Okay, I'm just going to have to dive that in and look at it because, yeah, so 2 to the power of 64.
Try it, scientific notation.
Woo boy. Yeah, it's essentially 2 followed by 19 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Okay, so anyways, you're not going to max out the capacity of a 64-bit operating system in terms of how much RAM, how many bytes of memory that program can access. That's a physical limit, not a operating system limit. Your laptop can, hold 16 gigs or something like that. And we're using the term kilos and gigs and stuff like that. So this is like 1.8 e to the 19.
Bytes.
Yeah, maybe. But on the other hand, that 4 super gazillion, quintillion, bazillion is probably enough RAM for the next couple of years, huh? So when we talk about RAM, bits are grouped into clusters of 8. They didn't have to be, but hardware manufacturers kind of settled upon 8-bit words in the 60s. And, they could have been 13. Some computers had really strange numbers of bits representing a piece of data. But people decided that they're grouped into groups of 8. Their 1 byte is equal to 8 bits. So if you have a 4-byte number, like an integer, it's
64 bits.
equals 32 bits. An 8-byte integer, which is a long, equals 64 bits. So that 4-byte number, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. It would have been easier if I'd put a little break there to make it easier to spot. I'm not sure I put it in the right place. Right. Like that. That's a 32-bit number. That's a 64-bit number.
That is huge.
So a 32-bit number can hold a value of up to about 4 billion. But that's 0 to 4 billion. If it was all ones, if our int was all ones all the way across, it would be about 4 billion.
You just copy and paste it.
So we have, didn't take me that much longer to type the ones. So we have the ability to count from 0 to 4 billion, but that doesn't support negative numbers. So what some clever computer engineers decided is that you could use this first bit as a so-called sign bit. And if the first bit was 0, it was a positive number. And if the first bit was 1, it was a negative number. And so that's how you get from negative 2 billion to positive 2 billion, is because you can use these 31 bits for the magnitude of the number, and then the next one dictates whether it's positive or negative.
Can you explain that?
Maybe if I use smaller numbers, I'm not going to be able to talk about it in terms of like. So if we have the ability of counting with 3 bits,
So do they use binary to describe trig functions in a way?
I don't know. Well, you could.
And use it as forms of amplitudes, and that's it.
Whatever formula you could express, in programming language, yeah. So we have the ability of counting if you have 3 bits from 0 all the way up to 7. But what if you need to support negative numbers? If you need to support negative numbers, you could use a bit in front of it to dictate whether it was a positive or a negative number. Now this is not strictly true. This is not 100% accurate, but it's close. What you could say is that these numbers represented that, whereas this, and they actually use something called 2's complement, would be -1.
Oh, so this is just like reading from right to left and use a reverse option of integers to zeros, right?
Well, it's not reading right to left, it's just using an extra bit to indicate that there's a minus sign in front of the number.
Okay.
So that would be -2, -3, -4, -5. And the computer engineer in the class is going, well, that's not true. But that's because it's silly to have the ability to specify -0, right? Positive 0, -0. So instead they do something called 2's complement. So it's a little bit different, but the first bit dictates that whether it's a positive or a negative number. If the first bit is a 0, it's treated as a positive number. If the first bit is a 1, it's treated as a negative number. So now with 4 bits, we have the ability to count from -7 up to +7. Or if using 2's complement, I think we can go up to -8 to +7. It's still a range of 16 different numbers. It's just that half of them are negative and half of them are positive based on that bit. Does that make sense? Is that a better explanation? Okay. Y'all are asking better questions than the last class did, so I appreciate that. It's keeping me on my toes.
I was actually asking, what do you mean by
Pardon?
like negative numbers?
Well, you know what negative numbers are.
I know.
Yeah. Yeah.
Why would the computer need to need that?
I don't know. If I need to add 3 times -5, the computer certainly needs to know how to hold -5 in its
So,
RAM.
for making a calculator or something.
Well, it's just to hold data. Humans, there's an infinite number of numbers. Half of them are negative, half of them are positive. The computer needs to be able to represent negative numbers versus positive numbers. But you're right, sometimes you don't need negative numbers. My age is not going to go negative. The patient's weight is never going to go negative, right? There are things that only have a magnitude without a sign, right? You can be the first person in line and the second person in line and the third, but you can't be the -12th person in line. That makes no sense. So, if that's the case, there are variables, which don't use a signed bit, right? The maximum value of a signed 4-bit number is just 7. It can't get any higher because by the time it adds that 1 there, it flips over and starts being negative. And do you remember when we were writing our doublers and it got up to 1 billion and then it tried to double it and suddenly it became negative? That's because of that bit, right? It got one more bit got turned on and so the number got turned negative. But if you don't need negative numbers, then you can use them like we were doing up here. Right? All 4 bits represent numbers. None of the bits represent signs. And so if you want to only use positive numbers, you can count twice as high. If you need negative numbers, you can only go half as high, but it supports negative. So those are called unsigned numbers. A signed int, which is just a regular int, can go plus or minus 2 billion. plus or minus 2 billion. An unsigned int, which is, you use the word unsigned in front of it, so I'm not sure why sometimes they get abbreviated uint, UINT, can go plus from 0 to 4 billion, but it can't go negative. So by using that bit for data, it can't go negative, but you can hold larger values. And we could demonstrate that. We could write our little doubling code, our loop that we used last time. Let's use a for loop this time. We haven't done a for loop yet in this class, to my recollection. I could be wrong on that. Are we on Lecture G like I think we are? I think we are. Oh, and I need to make a Dropbox so that you can leave when you need to. So let me do that.
Ooh. Oh my.
Why is it defaulting to January 2010? That's not helpful. Okay, so if you need to leave early, you can just upload a note saying that you were here. Hope you remember how to do that when you're looking at the Dropboxes. It's not mandatory to type in the notes. I do want you to fill out a lecture review form if you miss class, but when you're looking at your submissions, or when you're getting ready to submit something, one of the tabs that's available to you is not just a file, but you can do a text entry. And you can go, yo, I really love this class. Right. So you don't have to take notes. And I don't think there's going to be much to upload today. We're going to write the doubling program again, but I'm not sure if there's even a reason for you to do that. You've already written a doubling program a couple of times.
So release the class early.
Oh, I don't know about that.
Well,
We're not halfway done talking about binary and hex. So we're going to write the same loop that reset after it hit 1 billion, but we're going to make it an unsigned int, so it's going to be able to count higher. But I'm going to use a for loop just to be a little bit different. We've used while loops already. I need some number that'll keep doubling. Why don't I just call it x? Int x equals 1. And now for the loop. For parentheses, and I think I was using c as my counter, so I'm going to do that again. Int c equals 1 semicolon. C is less than 20 semicolon. C plus plus. Well, that's funny. And then curly brace. x equals x times 2, which you could abbreviate as x times equals 2 if you so felt the need. And then let's print it out. C out less than C less than quote space quote less than x less than ENDL. Now the for loop handles the incrementing, so I don't need to put a C++ down at the bottom of the loop like I did when I was doing a while loop. Instead it's just tucked up here. So it's like a for loop is a cooler loop because it specifies a starting point, it specifies a stopping point, and it specifies the increment all in one swoop. And by the way, I meant to make that less than or equal to. So I'm going to change that to C is less than or equal to 20. Then I'm going to run. All right. Doubling it 20 times got to 1,000,000. I think I recall that if we double it 30 times, it gets to 1,000,000,000. Yep, now it's at 1,000,000,000. And if you remember, if we did 31, it flipped to 2,000,000,000, and so it went negative. I'm going to make this like up to 33 and watch it go. A little bit larger. It wasn't able to get, yeah, see? It can't double 31 times. It flips to negative. Why is it negative? That sign bit, right? The first bit went negative, and then the rest of the bits, the 31 bits, are actually used to hold the magnitude of the value. But if we make it an unsigned int, if we go back in and modify this and we make this unsigned, not signed, unsigned, then it'll get a little bit larger before that happens. See you Tuesday. See, it got up to 2 billion. And really, it would get up to 4 billion if, you know, but not to 4.2 billion or whatever the double of 1 is. So by making it an unsigned value, it can go twice as high, but it can't go negative. So what do I mean by that? What if we set x equal to 0? It's an unsigned value. So if we subtract 1 from it, and then we print it out, what's it going to look like? It's not going to be -1. It's equal to the largest value that you can hold in 32 bits. We saw this number a while back when I did 2 to the power of 32, except it was a 6 there. So by going backwards, by going from 0 to -1, instead it went from 0 to the largest value possible. That's what happens when you don't have a signed bit. Usually we like the option to have negative numbers. There's no real reason to use an unsigned int unless you just think that you really need it to go that little bit larger and you're sure it's never going to go negative. But if you need it to go larger, what's the right choice? Make it a long, right? Then you still get your negative numbers. Alrighty, so we have seen that we can count up to 16, 0 through 15. So if we had this, oh, I guess I am going to demonstrate. No, we haven't done conversion yet. Powers, placeholders, like if you have this number in base 2, convert to base 10. Well, it's not 1,110.1. It's 2 to the power of 4, 2 to the power of 3, 2 to the power of 2, and 2 to the power of 1. And 2 to the power of 4 is 16.
9.
I have to go this way, sorry. 1, 2, 4, 8. That's how I can do it. It's just, you know, start doubling each time. There we go. So if we have the number 1010, it means 1 times 8 plus what times 4? How many 4s do we have? Don't have any 4s. How many 2's do we have? Got a 1 there. And how many 1's do we have? No 1's, right? So we could shorten that a little bit further, and we could say that we have an 8 plus a 2. And so that adds up to a 10. And if we scrolled way back up to when we were counting 0, 0, 0, 0 to 1, 1, 1, 1, we would see that a 0, 1, 0, 1, or a 1, 0, 1, 0 is in fact a 10. So what if we had, I don't know, let's do some more. I'm going to just write the places like this, 8, 4, 2, 1. What if we have 1, 1, 1, 1? What does that equal to?
This is 8, 4, 3, 1.
That's an 8 plus a 4 plus a 2 plus a 1 equals 15, the highest value that can be held in 4 bits. What if we have 0, 1, 1, 1? Well, 8, 4, 2, 1. Do we have any 8s? No 8s. So that's just a 4 plus a 2 plus a 1.
You put a 3 1 on the top one.
Pardon? Oh, you're right, I did. Okay, yeah, that's cute. There we go. All right. So, we can calculate the value of any 4-bit number pretty easily. And what if it needs to be larger than that, like an 8-bit number? Bytes go up to 8 bits. So what if we had this number? No, not 9s. Is that 8? 1, 2, 3, 4. No, that's 9. Let's take one more out. Okay. So if we have that in base 2, and we want to convert to base 10, we would just have to write out the powers of 2. 1, 2, 4, 8, 16, 32, 64, 128. That's 8. 8 different bits. So 1, 0, 0, 1, 0, 0, 0, 1. You saw where I got those. I just wrote that. Okay, so 1, 0, 0, 1, 0, 0, 0, 1 is what? 128 because of that. Plus no 64s, no 32s, 16. Plus no 8s, no 4s, no 2s, plus a 1. Equals, is that 135, I think, maybe? Alrighty. What if you had to go backwards? I'm never going to ask you to convert a base 10 number to base 2, because the process by which you do it is a little algorithm that you can follow. Back before I learned the algorithm, and it wasn't that long ago actually, I thought like this. Oh, I need to take the number 241 and turn it into base 2. Well, what's the largest power of 2 that'll fit into it? Well, 128 will fit. So I'm going to put a 1 in a 128 column, and I'm going to take 241 and subtract 128, and I'm going to get, and keep trying to do it like that. Instead, you do some interesting little algorithm where you keep dividing by 2. So if we have this number, 135, we're going to just keep dividing by 2 and take note of the remainder. So 135 divided by 2, rounded down, is 67 with a remainder of 1. Yeah, because it's 67.5, but we're going to round down each time to get a whole number. And so 67 divided by 2 is 33, the remainder of 1. Something's bugging me about this. I may not have done this right. 33 divided by 2 is 16 with a remainder of 1. And then 16 divided by 2 is 8 with a remainder of 0. 8 divided by 2 is 4 with a remainder of 0. 4 divided by 2 is 2 with a remainder of 0. 2 divided by 2 is 1 with a remainder of 0. And 1 divided by 2 is 0 with a remainder of 1. And then you write the number down. I had to have done something wrong. I did something wrong either here or here, so we're going to have to figure out which one's wrong, because these are not coming out the same. Yeah, did I just add this together wrong? Is that?
That's 145.
Yeah, it's 145. All right, let's do it again then.
Let's do it again. Doesn't use an eraser.
There we go. So 145 divided by 2 rounded down is what? 122. Remainder of 1. And then what's 122 divided by 2? Wait, it's not 122. Where in the world did I come up with that?
74.
It was 70 something.
74. 72.
Yeah, 72, remainder 1. And then 72 divided by 2 is what? Come on, guys. I know y'all can do that in your head. 36
Remain 0.
with a remainder of 0. And then what's 36 divided by 2? 18, remainder 0. 18 divided by 2 is 9, remainder of 0. 9 divided by 2,
4.
rounded down is 4, but we had a remainder.
1.
And then 4 divided by 2 is 2, with no remainder because it was an even number. 2 divided by 2 is 1, it was an even number. 1 divided by 2.
0. Remain 1.
Okay, and then you just write it down from the bottom up. 1, 0, 0, 1, 0, 0, 0, 1. Like that. And so that's what we have here. That's how you go from base 10 to base 2. And I'm not going to ask you to do that. I want you to know how to do this thing, though. I want you to know how to do those bits. So what I want you to do is to fire up Word, or maybe just Notepad. I don't care which you use. You can even just put it into your Visual Studio program if you did create it. But why don't we use, I don't care which one you do. Open up Notepad.
Open up Notepad.
Or whatever you want. And let's convert some 5-bit numbers. And here's the numbers that I want you to convert. And I'll do the first ones with you. The first couple.
I want to convert this number.
Okay, so we need the powers of 2 out to 5 places, which are 16, 30, no wait, it's 30, yeah, 16, 8, 4, 2, 1. So that first one is easy, right?
1.
If we just wrote 0, 0, 0, 0, 1, that's just 1, right. How's about 0, 0, 1, 0, 1, like the second one? That's equal to a 4 plus a 1. So that's a 5. All right. And then a 1, 0, 1, 0, 1. I want you all to figure that one out. You don't have to say it aloud. And then a 1, 1, 1, 1, 1. And then a 0, 1, 0, 1, 0. And I know that's a lot of typing, so I'll give you all a little bit of time. And the concept for that is if you have a series of numbers and you want to display that in some human readable format, what does that equal? Yeah, we could add them all up with powers of 2 and say that it's equal to 25 gazillion or something like that. But you want to be able to display it on the screen in some format that makes sense. So that clustering these things into 8 bits is how people decided to do it. But if you clustered them into 4 bits, you could do something called hexadecimal. What do I mean by hexadecimal? When we had these things here, from 0, 0, 0 up to 1, 1, 1, 1, we had the option of counting them as any value between 0 and 15. So if I take those numbers that I wrote, that big old long string, I could say that's, what is a 0, 0, 0? It's a 0. Yeah. I guess I have a lot of zeros in a row. Didn't mean for that to happen, but. And then what's a 1, 0, 0, 0?
8.
That's an 8. And the next one's a 10. The next one's a 15. Looks like I have two 15s in a row. And then what's that one?
12.
12. And then one more 0. Okay, that's great. That would work. We could display these numbers on screen. But there's kind of a problem. And what do I mean by that? If you wanted to condense it, right, you would not want to display a 0 followed by 4 spaces and a 0 followed by 4 spaces or whatever. Okay, so the problem is that some of these take up 2 spaces and some of them take up 1 space. So you don't know really whether that's a 8 followed by a 1 followed by a 0 or whether it's an 8 followed by a 10. So you have to actually pad them out to two places for this to actually work. You have to do that, 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 that. I'm going to have to do some deletions after I get this. Yep. Okay, so we could write that down now and be sure what we were looking at. 0, 0, 0, 0, 0, 0, 0, 8, 1, 0, 1, 5, 1, 5, 1, 2, 0, 0. All right. But that's a lot of wasted space, right? Most of these things did not need zeros in front of them. So if you were to display this on a screen because you had a whole bunch of bits, you had a whole bunch of zeros and ones on your, you had a whole bunch of vacuum tubes representing zeros and ones and you wanted to be able to print it out in some kind of numeric form, that's not really as efficient as if you could do it to where each one of these was just one character. Every one of these is 2 characters. The way they got around that is by doing something called hexadecimal. Hex meaning 6, des meaning 10, 16 digits. Well, how do we get 16 digits? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Well, that's 10 digits, but we need 6 more. Now, somebody knows what hexadecimal is and can tell me what we're going to finish this series out. We want to count to 16 using only single nodes. A, B, C, D, E, and F. So with hexadecimal, you wind up with numbers like 6F, or B3, or AA, right? Those are all valid hexadecimal numbers.
Don't we need G?
Well, not to get up to 16 different values.
Oh, because it's 0.
Yeah, exactly. You got it. You got it. Yep.
Okay.
Yeah. So, with these in place, we could condense that a lot. Let me go ahead and add the hex values in another column over here. I should just do it for like the last 6, right, rather than do them wrong. But nope, not 10. Yep, there we go. So, let me bring back our big old list of binary again. Except this time we're going to turn them into hexadecimal.
Turn all the hexadecimal.
All right, so 0, and then what's the next one?
0.
There's also a 0. What? No, 0. And then what's that one in hex? Well,
6.
it's no different than it was before. 8. And what's that one?
A.
A, exactly. And what's that one?
F.
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 F. What's that one?
C.
C, followed by one more 0. There's no need to add those extras, pad things out with extra zeros. So if we wanted to express that like that, we could. Half the space. So if we needed to put on paper the contents of a whole bunch of zeros and ones in memory, we could display them in hexadecimal.
I have a question.
Yes, sir.
Is this how the addresses are made for certain bits?
Uh-huh. You are probably familiar with the idea of IP addresses. An IP address, or a MAC address, MAC address is, how do I get the MAC address of a PC? Can somebody tell me that?
You gotta go to settings, control, whatever it's called. I have a Mac now, so this is so hard.
Is it IP config? Would that get me to it?
Control panel.
Yeah.
But you can, yeah, I went into IP config. It's not showing the MAC address, but what we're seeing is my IP address is 1055.10.220. Do these numbers look kind of familiar, the range? The largest it could be is 255. So the lowest IP address you could have would be 0.0.0.0. The highest IP address you could have would be 255, 255, 255, 255. So these are actually 4 bytes in a row. 4 bytes meaning 32 bits. They can be represented as hexadecimal.
So I have a question.
Yes, sir.
So what is next F?
What's after F?
Yeah, after F.
Yeah, if we're going to start counting, and we want to keep counting in hexadecimal, good question. 0, 0, 0, 1, 0, 2, 0, 3, 0, 4. I'm going to skip ahead, right. 0, D, 0, E, 0, F. We have maxes out. So it's going to turn into a 0, and what's going to happen in the next column? Except it didn't go to 2, 0. I made a mistake there. What should have the next one been? We don't reset back to 0 because we have more than 9 digits. We have 16 digits going all the way up to F.
Okay.
Like that. And then what's next?
Okay.
Serena, what's next?
That would turn into 2.
2, 0. Yep. Okay. So if you were going to turn a hexadecimal number, say you had this number, 1032.
Wow.
That's too large. Why don't we just do like 1F or 12F in base 16, and we want to turn it into base 10. Again, we need the powers. 16 to the power of 2, 16 to the power of 1, and 16 to the power of 0. Well, that happens to equal, I don't remember, what's 1616? Is that 256? I think so. No, it's not. Yeah, it is. Okay. 256 followed by 16 followed by 1. So if we have this number, 1, 2F, that means 256 plus 2 times 16, or actually it means 1 times 256, right? Plus 2 times 16 plus F times 1. But what was an F really? Way back when we were counting them out, an F
15.
was a 15, exactly. So we're just going to say that that's equal to, where'd my other note go?
Down.
Yeah. 15 times 1. So that's 256 plus 2 times 16 is 32 plus 15. I'm just going to copy and paste that into Google rather than do it in my head.
Have to change to 16.
304. 15. 303. I don't think I'm going to make y'all type in some hexadecimal numbers and turn them into decimal like that. But you can go backwards. If we had this, FEA 9, and we wanted to turn those into bits, we could do that. What is an F?
15.
Wait, where'd it go?
14, 1.
Yeah, so an F is 1111. And then what's an E?
1, 1, 1,
1110. And then an A, 1010. And then a 9.
1001.
All right. So I want y'all go back to your document and write out a series of bits that represents A92, OF7, and I don't know, F2, well, ACE. It's silly, but we could do that. All right, so y'all do that. Write down the 4-bit values that represent these hexadecimal numbers.
If you go back to the command prompt, if you type in
4-bit values.
Why would I go to the command prompt?
if you type back in get mac.
Oh, okay, cool.
/v. It'll give it to you. Space /v. Slash.
Oh, well, I think it did the same. Coolness. Yeah, we have these long sequences of hexadecimal strings. Okay, but anyways, I'll do this one and then I want you to do the other ones. An A is a what? It's a 1010. And then a 9 is a what? A 1001. And then a 2 is a 0010.
Cool. Type in keypad. 07E. I mean F. F7. 000. I'm gonna space it out.
So since a byte is 8 bits, any byte can be represented by a pair of hexadecimal numbers. And so when we typed in get max /v, each one of those is a byte.
The byte.
Yep, each letter here, each 2 letters represents a byte. Every 2 hexadecimal numbers represents 8 bits, so 1 bit byte. So that's a byte, 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 and so on.
You're a byte, you're a punch.
Is an address.
That's a good place to stop. And so a IP address is just a series of 4 bytes, and these could be represented with
Apparently the physical address
with
is supposed to be
hexadecimal.
your MAC address.
Yeah. Notice that doesn't really give you a lot of different choices.
Anymore.
You don't have a lot of different choices when you have only 4 bytes to represent all the different computers on the planet, all the different possible IP addresses on the planet. So they do routing and they do subnet masks and they've tried to squeeze in as much as possible. This is called IP4 because you have 4 bytes in each address. But they've pretty much maxed it out. The routers have to do a whole bunch of tricks. So they're going to switch over to something called IP6, where you have way more bytes. Not just 6, I think you have 8. IP version 6 gives you 8 bytes. So the number of different computer addresses you can have on your networks is astronomical. Let's stop there. I think our bits and bytes are about done. Except I want to mention that a kilo is 1,000. You've remember in physics, but in this language it's a 1024. And then a mega in physics is 1,000,000, but in this language it's a little bit more. And I'm just going to put million. And then a giga is 1 billion. And what's after that? Nowadays hard drives are sold not in gigabytes, but in terabytes. Yep, which are trillions.
And then petabytes.
And so on. Yeah. So they get larger and larger and larger. These are all in powers of 2, though, when you're talking about computer science. So it's not exactly 1,000,000. Something a little bit different. And it's not exactly 1 billion. It's a little bit different.
And when do you all talk about that type of stuff?
when you're buying your computer. When you're buying the hard drive, you need to know what a terabyte is versus a gigabyte or whatever.
It helps you find out which can have more memory and have more speed.
Yeah. All right.
You heard of a Yoda byte?
I've heard of it, and I forget how big it is.
YOTTA.
A yottabyte kind of sounds interesting.
It has 24 zeros on it.
Oh my gosh.
It's 2 T's.
So 2 to the power of 10. No, that's not right. 2 to the power of 10 is 1024. A kilo is 2 to the power of 10. A mega is 2 to the power of 20. A giga is 2 to the power of 30. And a tera is 2 to the power of 40. And a peta would be 2 to the power of 50, and so on.
And I think exia.
I love that. Yoda. That's funny. I'd forgotten that.
It's YOTTA.
Yeah.
2 T's.
Yottabytes. Where's gonna be a 1 yottabyte hard drive?
So it's 2 to the 80 bytes.
I don't doubt that's gonna happen.
How do you know that?
Probably like the Alienware
Oh, yeah.
Area 51 computer. You seen it?
Mm-mm.
It's shaped like a big triangle. The reviews on Amazon are funny because some people say like, I bought this for the country of Zimbabwe. I guess it's heat. And there's some other things, funny reviews. Like someone said they sold their house to get the
Yeah.
computer.
Cool.
It was like $8,000.
So again, we're going to weasel out without a homework assignment. So, because I'm not going to like give y'all a worksheet, although I've done that in the past. You know, convert these numbers from the one to the other. Next time we talk about this stuff, we're going to talk about sector editing. If you took a file and you needed to display its contents and it wasn't a text file, like what if it was a Word doc or an Excel file or a music file, MP3 file or whatever, you still might need a way to load it up and look at its data. And so you can use something called a hex editor in order to do that. Go ahead and upload whatever you want, or just a note saying that you were here, into the Dropbox.
Oh, a note saying, hey, you're here.
Yep, that's enough. But if you skip the lecture, I do want you to fill out a form, because I don't want you just going, I watched it. Right. You really do have to watch the lectures if you're at home.
But people are not going to get that message unless they watch the lecture.